All right, chapter 8, using calculus to optimize a function, not just algebra 2. But here, before we get going, it just is not at all a bad idea to tie what we're about to do into old stuff. So we're going to optimize a function. A lot of our functions are going to be cubic, like this. X is going to be some dimension or whatever, and then y is going to be some function like area or volume. And literally, we're going to say, well, we got this function. There's only a certain domain for which we can get feasible answers, anything that makes sense. And we're headed for that max point right there, and whatever that x is, that's going to maximize our function in this case. So as we construct meaning, tie it into something that we can visualize and understand better. Here's the 4 steps that I would promote. Step number 1, just identify the quantity that we're going to maximize or minimize in the word problem. Don't get distracted by other information. We'll use that later. A lot of it's going to come down here, but it's fine. Now, number 2, in tandem. So do these things like simultaneously a lot of times. You're going to draw a diagram and you're going to create a function. Use as many different variables as you want. Don't worry about it. If you try to make substitutions now, it just complicates the situation. So don't do it. Use as many variables as you need to and go back and forth from drawing a diagram to get a feel for what you have and then writing the objective function. So we'll do that, but I just want to spell that out. Number 3, after you've written a function using as many variables as you need to in step 2, now write the function as the function of just one variable. And now's the time when you're going to be using the other information given in the problem to do things like defining y in terms of x, that you can make a substitution, or even a third variable in terms of x if you need to make the substitution. And then step 4, do the calculus that you do so well and find the first derivative, set it equal to 0, find our critical points. We are after that dude right there. All right. So let's suppose you have a stone wall and 400 feet of fencing to construct a rectangular pen construct a rectangular pen that you're going to use to enclose hyenas, okay? Because hyenas, they're a lot of fun, okay? They're always laughing or whatever, and they're kind. So, you know, even hyenas, you put them in this pen together, they write little notes every day to tell each other how much they appreciate them. They become pen pals. It's true, all right? In addition, you can name them cool names like there goes Taffy, you know, or there goes Snickers. And so you say, oh look, it's Laffy Taffy and Snickers. Snickers is stubborn, no, I'll tell you, man. He just lays down, won't move. Come on, Snickers, not going anywhere for a while. He's annoying, but we're moving on. Here we go. All right, find the dimensions that will maximize the area. So we go through the first 3 steps of the problem. The first step, I know that's going to be important to 400 feet, but I'm looking for, find the dimensions we need to do what? To maximize the area. Woohoo! We're going to be doing an area function as our objective function. We're done with step 1. Step 2, now we're going to draw a diagram. We're going to come up with the function all in the same step. This one's pretty easy. We probably don't even need, let's do the diagram. Here it is. We got a wall. There's the wall. And then we know we have to use the wall along with the fencing to enclose 400 feet. We'll get to the 400 feet in a minute. What we need is, we have this wall right here, and you know, I'm going to cheat and tend to call this x and this y. We could do x here and y there. We're just going to, look, we got lucky. We did x there and then y. All right, so it's, okay, that's a picture. That's our diagram. We need an area function. And right now, our area function is going to be a function of 2 variables. I think it's a good habit to get into to start using a meaningful letter for our function. And it's okay to have a function of 2 variables right now. It's fine. We know that this is a rectangle and the area is base times height. So we're just going to have x times y. There we go. We're done with our first 2 steps. Step 1, maximize the area. Step 2, draw a diagram and make sure it matches up with our function. And I don't care that we've used 2 different variables. Now we go to step 3. Now's where we need to get this function down to just 1 variable. So we need it to be a function of just x. Now here's where this information comes into play. Altogether, the total amount of fence when we start here and go all the way around the pen has got to be 400 feet. So we could say, okay, if I draw a little equation to describe that amount of fence, it would be that I have an x plus y plus x equals 400. That's what that information is telling me. Now what I want to do is use that relationship between x and y to solve for y in terms of x, so I can replace y with that expression, that algebraic expression, in the original function, taking it from a function of 2 variables to a function of just 1 variable. So let me solve for y. Right now x plus x is 2x, so I'm going to subtract 2x from both sides, and hopefully you can see then that the relationship between y and x is that y has to equal 400 minus 2x. So we could go up here and say, oh yeah, this guy is 400 minus 2x, and that makes sense to us. We start out with 400 feet of fence. If we take away this side and this side, how much is left? Well, you start with 400, you take away 2x. So that third step is saying use the other information, solve for y in terms of x. Now we can rewrite the function as the function of just one variable. It's x times an equivalent value for y in terms of x that we got from that other piece of information. So what are we trying to maximize? Area function. That tells us the function we're going to need. Draw a diagram, write the function 2 variables, make the substitution. Now we're rocking and rolling. Okay, so here is our function, and I would say this. Despite using a calculus approach to maximize, a quick connection to algebra is not a bad idea. So if we really thought about this, we could realize that, you know what, if we were going to graph this parabola, if you expanded it out, right here you'd see that you got a negative 2x squared, leading coefficients negative. So that implies that we have a parabola opening downward, and if you wanted to find where the roots were, set this equal to 0, x would have to be 0, and x would have to be 200 to make this thing 0. So we could realize that our roots would be at 0 and 200 feet, and it's a parabola opening downward. So that's a heck of a parabola right there. So we'd realize, you know what? I know the answer to the problem before I even use calculus. I'm going to maximize the area because the y value is the area as a function of x. I'm going to maximize the area at 100. Dang, I know the answer before I even proceed. But it ain't a bad idea to just get a feel. Again, making connections, constructing meaning to help us through the process. It really helps us to be better mathematicians and stronger problem solvers. So here we go. We continue with the problem though. We're going to use a calculus approach. Now, to use the calculus approach, we need to set the first derivative equal to 0. So when we find the first derivative, I think we agree, instead of using a product rule, it's usually better to take it out of factored form and put it as a polynomial with, in this case, 2 terms. So once we distributed and we got this, hey, the first derivative is pretty easy. We can see that our first derivative of this is this guy right here. So we need to find the x value of the critical point, set the first derivative equal to 0, do a little bit of algebra, and cha-ching, it's 100. And then again we say, is that a max or a min? But because we thought about, it's a parabola opening downward, we know there's only one critical point on a parabola, it's at the vertex, and if the parabola is opening down, the vertex is the location of the maximum value of the function. So we know that's our max value. Now remember, we're trying to find the absolute max within the feasible domain where we have to obey information like we only have 400 feet of fencing. So again, we really kind of need to think about what that function would look like. The endpoints in the feasible domain are 0 and 200. Hey, those endpoints will give us the absolute mins in this interval, and the absolute max would be at the x equals 100. So life is good. We solved the problem. We put 100 in there. Can't remember if we're starting a new problem or we're going to start a new problem. So if you put the 100 back into the original function, this would give you 400 minus 200. That's 200 times 100. That's 20,000 square feet. Those heinies are going to be pretty happy, man. They got 20,000 square feet to roam around in. So there we go. Let's go to a new problem. Let's make it a little bit more difficult. Let's suppose that we have a rectangular box with a square base and it has no top. I don't know, maybe the top just has like a bar going across it. Hold it, that's no good, because then it would be a topless bar, and that is not appropriate in a high school math class. So there's just an open top, there's no bar on it. All right, here we go. We want to maximize the volume of the box if it is to be constructed with exactly 96 centimeters squared of material. Okay, so that's good. We ignore this because that was stupid. And then all we do is we say, step one, what quantity are we maximizing or minimizing? I don't know about you, but I'm focused on that word right there. And then this, the volume, woohoo, we're going to maximize volume. We're happy campers, we're moving on. So now what we do is we say, okay, remember what we need to do. It's volume we're going to maximize, so we need to come up with a function for the volume and draw a picture to help us get a feel for all this and write our objective function. Hey, this is a pretty good picture. We have a square base on a rectangular prism. It looks like a toaster, I know, kind of crusty, but so we got a square bottom, that's an X. Clearly that's an X, yes, and an X, and then that's a Y. So it's like, oh, okay, hey, listen, the volume is of any prism, of any right prism, is to take the area of the base and then multiply it by the height. So this is kind of a no-brainer. We're going to say the volume is X times Y. We are done with steps 1 and step 2. There's our function, but we now need to write this function in terms of one variable and one variable only. Right now it's a function of both X and Y. So it's at this point that we need to now convert to a function of one variable that we go grab the other information from the problem. If we go back, we are reminded that altogether we have 96 centimeters squared of material. Now don't make any assumptions about that. This may seem like one of those problems where you have a square sheet, you cut out the corners that are X by X and fold them up. That's not what this problem told us to do. It just said that in the end, all the material you have to make this box needs to add up to 96 square centimeters. And you might need to stop and think for a sec until you realize what they're giving us is surface area. That's really the constraint that we have. The total surface area, if you have little pieces of sides, is all together, the sides have to add up to 96 centimeters squared. So now a good idea would be to, again, use our diagram and think about what would that mean that the surface area would all have to add up to 96 centimeters squared. Well, think about this. Because it's a topless box, we have 5 sides. We have the base, and hey, the base is X by X. That's how we get our area for the base, so that's X squared. And then each side, each of these vertical sides would have a base of X and a height of Y. A base of X and a height of Y, and we have 4 of those sides. So each of those sides would have an area of X, Y, and there would be 4 of those sides. So what it means is that it must be true that our X that we use, if we square it, and we add to that 4 times X times Y, then our total surface area for those 5 sides would have to equal exactly 96 centimeters squared. There it is. That's like the secondary equation that we're going to use to solve for Y in terms of X. And Alan was right. I think Alan or Josh, one of the two, said the other day, hey, you know what? This is just like doing the substitution method in solving a system of equations. And I couldn't agree more. All right? It's just that that is the more important equation or function. We're going to use this guy to make a substitution of that bad boy so that we end up with, ding, a function of volume that just has X in it. So what we need to do is we need to solve for Y right here. So we're going to subtract the X squared. We're going to be left with 4X times Y is equal to 96 minus X squared. We're going to get Y by itself by dividing both sides by 4X. And so we're going to say, okay, Y is equal to 96 minus X squared divided by 4X. And we might as well just leave it like that. A lot of times it's not really worth it to simplify that in algebra, especially as we're about to make the substitution. So we are ready to finish up with step 3. We use the secondary information to say Y must equal this guy right here. So where we see the Y, we'll replace it with this, and we will only have X's in our function. So step 3, we will now have a volume function of just one variable X. It will be X times X, which is X squared, times Y, which we know is 96 minus X squared divided by 4X. So this would be our volume function. Now let's clean it up a little bit. We only have X's in there, but let's clean this bad boy up. We can cancel one of these x's with one of those. So we're going to have x times 96 minus x squared all divided by 4. And I would argue that we should probably just clean it up just a little bit more and say it's x times, split this into two fractions. 96 is being divided by 4 minus x squared is being divided by 4. So 96 over 4 is 24 minus the x squared divided by 24. So, right, divided by 4, sorry. So just divided by 4. So there it is. That's about the way we'd want to leave it. We're done with step 3. We have our objective function for volume in terms of just one variable x. So now we proceed. Now it's time to do a little calculus. So we say, all right, here we go. There's our volume function of x. It's right there. And so, oh, by the way, if you see what I did, sorry, I distributed this out. So I went ahead and distributed the x here. That's why it's going to be 24x minus x cubed over 4. I really should have done that because I was going to anticipate, right? We should have anticipated, I should have, that hey, we're going to take the first derivative and it's better to take it out of factored form and into this form here as a polynomial, easier to take the derivative. So here we go. First derivative is 24 minus this bad boy right here. Now we're going to set that equal to 0 to find the critical points. Let's add this amount to both sides so we get it over here. We have this guy. Let's just do simple math in our head. How about we multiply both sides by 4 to get rid of that? If we do, we have 96 equals 3x squared. Let's divide both sides by 3. We get 32 equals x squared. Let's take the radical of both sides. There isn't any such thing as a square root sign. It's a principal square root sign, giving us, of course, the absolute value of x. Let's split this guy into a perfect square, a radical of a perfect square times radical of 2. So we're going to be left with x equals plus or minus 4 radical 2. The question is this our maximizing value? Is it within our feasible domain? Is it our absolute max? So to answer that question, let's go here. So we have, this is our volume function. This is our volume function in factored form. Now, here's what we would like to realize. The feasible domain is dictated by needing exactly 96 square centimeters of material. The nice thing is, when we made the substitution of an x quantity for the y, it was based on us obeying the 96 square centimeter thing. So that information ends up in our objective function, mathematically. So that's why, if we think about it from a mathematical algebraic standpoint, all we need to do right now is take our volume function. I chose to put it in factored form because what I want us to see is, don't do it, what I want us to see is that where the feasible interval for x is, where the roots are of the function, and then where are we in the first quadrant where we could get answers that actually make sense for us. So see what I did? I said, okay, we're going to use the zero product property, set the equation, the function equal to 0 to see where the roots are. There's a no-brainer, either x is 0 or this whole quantity here is 0. And if we do the math, 24 is going to equal x squared over 4. Multiply both sides by 4, we get x squared is 96. Take the radical of both sides, cha-ching! We end up with x equals plus or minus 4 radical 6. What the heck, we might as well just relate to it better by using a calculator. It's going to be about plus or minus 9.8. So then what we realize is we have 3 roots, negative 9.8, 0, and positive 9.8. So if we quickly sketch that function, we know it's a cubic that has a negative coefficient, and so it's actually going to be coming down and hitting this negative 9.8, swinging back up to hit the 0, then coming back down again to hit the positive 9.8. So what this function is going to look like is it's going to come down here, it's going to swing up yonder, and then it's going to do like that. This, right in here, would be our feasible interval for x. Those are the only values for x that would make sense in the context of our problem where we're building a box that has the right amount of volume to it. And like we said at the outset, our maximizing value would be at the place where we would hit the highest point on the y-axis, because what y is in this case is the volume as a function of x. So the higher the y, the greater the volume of the box that we're making. So where is this maximizing point? we saw that it was the 0.4 radical 2, which is definitely within our region because 4 radical 6 is way over here. So that is the value where we will find our maximizing volume. It is achieved right here. So when x is 4 radical 2, so we could put that into the function. We don't have to necessarily use a calculator until the very end, where we get this, and then, okay, go ahead, use the calculator at some point. But what that means is, when we use this for the x length of the base of that square on the square prism, on the box, we're going to end up with the best area, or volume rather, that we could get, which is about 90.5 cubic centimeters of volume. So, to summarize, here it is. Here's the approach, but please be ready to synthesize, you guys. We got to be ready to take what we're understanding about this and soon apply it to other objective functions, cost functions, profit, surface area, other things, products of integers, but here it is. Here is our approach. Step 1, what are we supposed to maximize or minimize? Ignore the other stuff for a moment, just so you can isolate that. Whatever it is we're trying to maximize or minimize, that in step 2 is the function we're going to write, area, volume, whatever. Use as many variables as you need to. Don't worry about that yet. Write the function in terms of multiple variables, and at the same time you might need to be drawing a diagram just to help you visualize and make sure that you're showing the components accurately. Once you've written the objective function using as many variables as you need to, then I would suggest the third step is to rewrite the objective function using just one variable, and you will do that by using the other information given in the problem, like 96 cubic centimeters, or I'm sorry, 96 square centimeters of surface area, and what else do we have, 400 feet of fencing or whatever. So use that other information to rewrite the function in terms of one variable, and then finally use the calculus really with an eye on algebra, all right, to find critical points. And really, if you think about what we're doing now, if you tie this back in to what we did in chapter 7, do you understand that we're finding absolute maxes and mins over intervals? We have to be in the habit of not only checking where the critical points are the maxes, but also the endpoints of the intervals. For now, in these simpler problems, no way the endpoints are giving us the max volume, but it is a procedure that we have to be cognizant of and doing all the time. So there you go. That's the beginnings of using calculus to optimize functions.